Our ultimate goal in this lesson is to talk about derivatives of logarithmic functions, but before we jump into that, it's probably a really good idea to go back and review some log properties from algebra. And the reason for that is that simplifying log functions before differentiating can quite often make the calculus simpler, and in some cases much simpler. So it's definitely worth our time to go back and look at some of those properties that might make the calculus easier. So before we get to our ultimate goal, let's just pause and talk about the algebra of log functions that you've covered in previous courses. We can't reteach the course, but I do want to point out that in any algebra course that you've had as a prereq, you've covered logarithms and you've come up with these properties and you've used them before and you've worked with them before, but you may not be as familiar with them on the top of your mind as you should be. So I just want to go through these very briefly and remind you that you have to bring these back to mind if you want to make the calculus much easier. One of the basic facts is that when you write the log of x base b equal y, that's equivalent to an exponential equation, b to the x equal y. And you spent some time in previous algebra courses with problems that tell you to change from one form to the other. You also came across the irrational number e, which is about 2.71828, similar to pi in that it's irrational and it has an infinite decimal representation, which is why we use a symbol for it. You're also familiar with the fact that you can use that number e as the base of a logarithm. And when we say a logarithm of x base e, we often shorten that to just ln x. So anytime you see ln, you can think of that as a logarithm base e. Extremely useful properties. Get these back in your mind. The log of a product is the sum of the logs. If it's base b, or if it's base e, which uses the ln notation. The log of a fraction is the log of the numerator minus the log of the denominator, again, whether you're using log base b notation or natural log notation, the ln. If you take the log of something to a power, the power can be brought out front. Again, whether you're using the notation log base b, where b could be any positive number base, or if you're using the ln, which is base e. Again, these are very useful in simplifying some of these expressions before differentiating, which makes our life easier, at least the calculus part easier. And I'm going to end this pre-discussion about properties of logs with some just basic facts that if you have them in your head at your disposal, it's going to make your life so much easier. First of which is that the logarithm of 1 is always 0 no matter the base. And again, if that base is e, you could write that same property as ln of 1 is always 0. If the base matches what you're taking the log of, in other words, the log of b base b, it's just 1. And if you translate that into base e, that becomes the natural log of e is always 1. The logarithm of b to the x base b is just x. In other words, if you're taking the log of an exponential expression and the base of the exponent is the same as the base of the logarithm, you just get the exponent for the answer. And if you translate that into natural log notation, that says natural log of e to the x is equal to x. And remember, x can stand for anything. So the natural log of e to whatever's up there is just whatever's up there. The last couple of really useful formulas. If you take b to the logarithm of x base b, again, the base of the exponent matches the base of the logarithm, you just get what you're taking the log of, which is x. And again, if you translate that to base e, that becomes the property that says e to the natural log of x is always x. Please get some of these basic facts back into your head so you can easily access them as you're working some of these problems. Before we get to the calculus, let's practice this a little bit. I'm going to throw those properties back up there so we can look back at them. So I could give you a property like simplify the logarithm of 8 base 2. Well, all these properties have to do with bases matching each other. Well, 8 and 2 don't match each other, but think about it a minute. 8 is really 2 cubed. So if you think of 8 as 2 cubed, that logarithmic expression becomes the log of 2 to the third base 2. Now the bases match, and you have a property that says, I'm actually going to do this 2 different ways, so bear with me. I'm doing it both ways on purpose. Actually, there are 2 reasons I'm doing it 2 ways, but this is the way I chose to do it first. You have a property that says if you're taking the logarithm of something to a power, you can bring the power down front. So that becomes 3 times the log of 2 base 2. And then you have a property that says if you're taking the logarithm of something and that something is the base of the logarithm, you always get 1 for the answer. So the log of 2 base 2, the log of 7 base 7, the log of 50 base 50 will always be 1. So the answer is 3. The reason I put this problem in here is that this type of manipulation can be really useful for some of our derivative problems that we'll do in a few minutes. And it allows us to take this, what I maybe call a strategy, for lack of a better term. If you want to write something, the log of something to a power, you can always bring that power down front. That in itself, right by itself, is a very useful property or strategy that will help us make derivative problems with logarithms easier in a lot of cases. So keep that in mind. Now, I said I was going to work the same problem a second way that's actually faster. I did it this way to show you sometimes there are multiple ways of doing things, but I also did it this way to show you that little aside about it being a useful property for derivatives. But if you actually were just trying to solve this problem in the fastest way you could, if you still think of the 8 as 2 cubed, we have a property that says if you're taking the log of something to a power and the base of the exponent matches the base of the logarithm, you just get the exponent for the answer, and so you get 3 immediately if you use that property. You can see it works either way. And that happens in a lot of cases, that sometimes you can get to the same result in different ways. The first way is a really useful strategy for us later on doing derivatives. The second way is actually the fastest way to answer this particular problem. And keep in mind, the natural logarithm is just a log with base e. So anything we say about base b also applies to natural logarithms because e is just a particular b. How about this? Simplify the natural log of e to the third. Again, we have a property that says when you're taking the natural log of e to a power, the answer is just the power. How about this one? Simplify the natural log of the fifth root of e. Well, we don't have any properties that deal with radicals, but we can think of the radical as a fractional exponent. We've been doing that. So if you think of that the fifth root of e as e to the 1/5, now the property that says the natural log of e to the x is x applies, and you can see that the answer is just 1/5. It would benefit you a lot to go back and think about these and make sure you have them in your head before you start the calculus material that we'll get to shortly. How about this? Write the log of x times the square root of x minus 1 base 2 as a sum. If you look back, there's a formula involving a sum, and it says if you take the log of a product, you get a sum. So if you take the log of x times the square root of x minus 1, you can write that as the log of the first factor, which is the x, plus the log of the second factor, which is the square root of x minus 1. How about this? The log of a fraction, x over the square root of x minus 1 base 2. Well, you have a property that gives you that as well. If you have the log of a fraction, you can write it as a difference. The log of the top minus the log of the bottom. Evaluate log of 16 base 2 without a calculator. Well, again, we have properties that tell us how to simplify some of these things if the bases match. Well, 2 and 16 don't match each other, but similar to the 8 that we did a minute ago, 16 is a power of 2. If you think of 16 as 2 to the 4th, now the bases do match, and you can use the property that says you can bring down the 4. You could have also done it by the other property that says if the bases match, you get the exponent for the answer. Either way, you get the same thing. How about this? Evaluate 1 over 27 base 3 without a calculator. Well, that's the log of a fraction. So you're probably going to suspect that, well, I could write it as a difference, and you could. There's actually a simpler way. 27 and 3 are not the same, but 27 is 3 cubed. So what if I wrote that as the log of 1 over 3 cubed base 3, and then change that 3 to the third to 3 to the minus 3 by pushing it up to the numerator, and that would change this whole thing into the logarithm of 3 to the negative 3 base 3, and now the exponents match up. Now the bases match up, and you get the exponent for the answer, so the answer will be negative 3. Go back and practice these and look at them. Write them down, see if you can work them out, and make sure you understand them. You can come back here and confirm that you're doing them right, and get these back into your head. These properties will help you with the calculus that we're about to get into. Speaking of which, let's start the calculus. Everything we've done up to now is just a review of some of the algebra of logarithms. It has nothing at all to do with calculus. Sometimes students get confused and they do all this algebraic manipulation to something, and they forget that they have not done any calculus yet, and they just stop. But if there's a calculus problem, you have to do a derivative, something like that, and you've only done the algebraic manipulations, you're not through. You've just gotten the problem into a shape so that you can do the calculus. So be careful when you're doing these problems to not think you're done when you've just done the algebraic manipulation that allows you to do the calculus. And you'll see what I mean. I'm just going to go ahead and put out the derivative rule that you'll be using. The derivative of the natural logarithmic function, and again, in calculus, we basically use base E. Sounds kind of funny to say it that way, but we typically use base E because it makes our calculus formulas much simpler. So we'll most of the time use natural logarithms because they just make the calculus formulas come out easier. And the first derivative formula stated in terms of natural logarithms says the derivative of the natural log of u is equal to 1 over u times u prime as long as u is greater than 0. Remember, you can't take the log of a negative number or 0. So whatever you take the log of has to be positive. And so this u greater than 0, you don't have to necessarily write it down every time you write this rule down, but you have to keep in mind that you cannot take the derivative, you cannot take the logarithm of 0 or a negative number. They have to be positive. But the basic idea is the derivative of the natural log of something is 1 over that something multiplied by the derivative of that something. Now, most of the time, I like to write that formula slightly differently. And I like to write it this way. If you think of u prime as u prime over 1 and then multiply top times top and bottom times bottom, that formula can turn into something to me that's easy to remember. It's just u prime over u. So the way I like to use this formula most of the time is think of it this way. The derivative of the natural log of u is the derivative of u over u. Both formulations are the same, and if you prefer one over the other, go for whichever one makes the most sense to you, but this is the one that I use most of the time. The exception is if u is really complicated, sometimes I'll write it the first way. But as long as u and the derivative of u are fairly simple, u prime over u is the way I like to think of this. As always, this u is thought of as being a function of x or whatever the variable we're differentiating with respect to. In this case, we are differentiating with respect to x. U is thought of as a function of x, but if u is just x, you can write that formula without the chain rule kicking in. And if you really are taking the natural log of just x, the formula is even simpler. It's just 1 over x, because the derivative of x is 1. So if you wrote x prime over x, the derivative of x would be 1, and you just get 1 over x. So if u is a true function of x, you have to think of it like this. If it really is just x, the derivative of natural log of x is 1 over x. Okay, so that's the formula, one of those two variations that we'll be using to do these problems in this section. So, jumping right in, first one is to use the derivative formula to find the derivative of f of x equal the natural log of the quantity 2x squared plus 4. It's not hard to figure out what to do. You're going to think of that 2x squared plus 4 as being the u in the formula, and then you go back to this formula up here and you write u prime over u. Well, u prime is the derivative of 2x squared plus 4, so it's the derivative of 2x plus 4 over 2x squared plus 4. The derivative of 2x squared plus 4 over 2x squared plus 4. Well, the derivative of 2x squared plus 4 is just 4x, so the answer is the derivative is 4x over 2x squared plus 4. See how simple this is? You really don't even need to put that step in there. You can go straight to the answer. The derivative of the natural log of 2x squared plus 4 is the derivative of 2x squared plus 4, which is 4x, over 2x squared plus 4. How about this one? Well, this one has a little complication because you have a natural log of x in it, but the natural log of x is one factor. This is really a product rule problem where x is like the u and the natural log of x is like the v, and when you get to the point where you're taking v prime, that's when this derivative of the natural logarithm formula kicks in. But overall, this is a product rule problem. The product rule problem says you take u times the derivative of v. Well, v is natural log of x, and according to the formula just above, the derivative of the natural log of x is 1 over x. Plus, then you reverse it, you take the v, which is the natural log of x, and multiply it by the derivative of x, and the derivative of x is just 1. And obviously, x times 1 over x is just 1. And 1 times log x is just log x, so you end up with the derivative of 1 plus the natural log of x. This is not difficult, but you do have to have some basic things in your head, and you have to practice to make sure you don't make careless mistakes, or at least to minimize those. How about this? Use the derivative formula to find the derivative of f of x equal natural log of x over x. Well, this is a fraction, so this will be a quotient rule. Low times the derivative of high minus high times the derivative of low over low squared. So that's low, which is x, times the derivative of high, which is natural log of x, minus high, which is natural log of x, times the derivative of low, which is x, and then over low squared, which would be x squared. And of course, the derivative of natural log of x is 1 over x, and the derivative of x is just 1, so you end up with x times 1 over x, which is just 1, and 1 times log x is just log x, so you end up with 1 minus the natural log of x over x squared. Again, you're overall doing a quotient rule, but within that quotient rule, you have to use the derivative of the natural log formula. It's not difficult, but it probably is going to require you to practice a bit to get used to the ideas. Another. What if the function is f of x equal the natural log of the fifth root of the quantity 4 minus 3x? We hit on this earlier when we talked about algebraic manipulation. This is the point that I was making earlier. The calculus will be much easier if you do some algebra on this function first, and you realize from an earlier discussion that a fifth root is the same as a 1/5 power. And then thinking back, you have a formula that says the natural log of x to a power, you can just bring the power down front. Well, that's where the 1/5 comes in. You can take that 1/5 and bring it down front, and you'll end up with 1/5 times the natural log of the quantity 4 minus 3x. Now we're at the point where I was making a point earlier that some people get to the point where they've done all this algebra and say, okay, that's the answer to the question. just be careful. This is algebra. Those are algebraic manipulations of the original function. We've done no calculus yet. We've used algebra to get it into the form so that we can then do the calculus, the derivative. So we're not done. We've just manipulated the function into a form where the calculus will be very easy. So all you do to take the derivative is, we have a formula from a long time ago that a constant times a function has a derivative. You can just write the constant down and multiply by the derivative of the function. So by far the easiest way to think about this is just write the 1/5 down and multiply by the derivative of the function of x, which is a natural logarithm. So we just write the 1/5 down and concentrate on taking the derivative of the rest. We're going to take the derivative of the rest. Well, what is the derivative of natural log of something? Well, that takes you back up to this formula. The derivative of the natural log of u is u prime over u. Well, what is u prime? Write the 1/5 down times u prime. What's the derivative of 4 minus 3x? Well, it's just minus 3 over the u itself, which is the 4 minus 3x. And of course, if you want to clean that up a little bit and write it as one fraction, you can think of taking the 1 times the 1 times the minus 3, and then take the 5 times the denominator. And you end up with minus 3 over the product of 5 and 4 minus 3x. And there you go. Practice makes perfect. Let's do another. This is a log of a fraction, so f of x is the natural log of x over the quantity x squared plus 2. And again, when you recognize the log of a fraction, you're probably going to want to rewrite it as the log of the numerator minus the log of the denominator. It makes the calculus much easier. So that's going to be the log of x minus the natural log of the quantity x squared plus 2. And you can see that's going to make it much easier to find that derivative, because at this point, the first one is just natural log of x, and I know the derivative of natural log of x is 1 over x. And the second one, if you think of the x squared plus 2 as being the u and apply this formula right here, you end up with u prime over u. Well, u prime is 2x over u, which is x squared plus 2, so you get 1 over x minus x squared over the quantity x squared plus 2. You could get a common denominator, simplify it, and write it more compactly, but this is fine. WebAssign's okay with this. I'm okay with this. It's a perfectly legitimate way to write the answer. We're working a lot of problems because there's so many variations, and I want to emphasize the fact that all these go back to earlier things, and if you're not good with the earlier things, it's going to clog you up and slow you down as you work through the newer stuff. So this is again a log of a fraction. It's a more complicated fraction, but the principle applies. The log of a fraction can be written as the log of the numerator minus the log of the denominator. Again, that's algebra, not calculus. You haven't done any calculus yet. But now it's in a form that I'm ready to take the derivative and use my log formula. So I've got a log minus a log, so I attack each one separately. If I want to take the derivative of the log of 2 plus x cubed, I get the derivative of 2 plus e to the x, not x cubed. I get the derivative of 2 plus e to the x over 2 plus e to the x. And then when I'm doing the derivative of the natural log of 2 minus e to the x, I get the derivative of 2 minus e to the x over 2 minus e to the x. Now you might not even want to write this step. I'm just doing it for emphasis. You might go ahead directly and just go ahead and put in what the derivatives are. The derivative of 2 plus e to the x. Well, the derivative of 2 is obviously 0 because it's constant, but what's the derivative of x? What's the derivative of e to the x? Well, we just learned that. The derivative of e to the x from the last section is e to the x. So when you take the derivative of 2, you get 0. When you take the derivative of e to the x, you just get e to the x. So that just gives you e to the x. And then when you move over to the second numerator, the derivative of 2 is still 0. But then you've got minus the derivative of e to the x. So that's where the minus sign comes from. It comes from right here. So you get e to the x over the quantity 2 plus e to the x minus a minus e to the x over the quantity 2 minus e to the x. And you can think of that minus as being brought up front, of course, and that minus, a minus becomes a plus. And that's a perfectly good way to leave your answer. Practice, 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 and when necessary, go back and get better at some of the earlier formulas, because when you bring them forward and use them, if you're still struggling with them and you throw them in the middle of new stuff, it just causes more and more difficulty, and it just gums up the whole system. So you've got to get good at the earlier stuff. How about this? Find the derivative of f of x equals x times the natural log of e to the power of x to the fifth. Now that looks horrible, but there's a trick that makes this problem so easy, because this is the natural log of e to a power. Forgetting about the x for a minute in front, the second part is the natural log of e to a power. You've got something that tells you that can be simplified. You've got that property that says the natural log of e to a power is just a power. And anytime you're using the same variable in the formula in the original problem, this problem's got x's and this formula has x's. If it helps you, you can think of the x as being a u. It doesn't matter. You can let the letters be anything you want to. But the point is, the natural log of e to any power, the answer is just the power. Well, this second factor here is the natural log of e to a power. So the answer is the power. But that x is still sitting there. So this x is still sitting there. But this whole natural log, this whole thing that I put in this box is just, according to our algebraic manipulation rules, it's just it's just x to the fifth. Well, that's wonderful. The whole logarithm goes away. So this problem had a logarithm in it and an exponential in it. But because of the way it was set up, the whole natural log and exponential just cancel each other out, and you end up getting rid of the logarithm and the exponential all in one fell swoop, and all you're left with is x times x to the fifth, which we all know is x to the sixth. Again, don't celebrate too early. We haven't done any calculus yet, but we've used algebra to simplify the formula, first of all, but it happens to, in the process, get rid of all the natural logs and exponentials, so you're just back to doing a simple derivative as you learned way long ago. It's just a plain old power rule. If f of x is x to the sixth, the derivative is going to be 6x to the fifth. So that problem that initially looked pretty horrible turned out to be one of the simplest problems we've worked yet, and that comes from knowing your algebraic properties relating logs and exponentials. Now this same process can work with implicit differentiation. All the old stuff still follows forward. So in this problem, we've got a logarithmic expression as part of an implicit differentiation problem. So it says, given the natural log of the product of x and y plus 8x equal 10, find dy over dx implicitly. Well, I know the log of a product can be written as a sum, and that's been helpful in past problems we've dealt with these logarithms and taking derivatives. I'm going to do it again. I'm going to write the log of x times y as being the natural log of x plus the natural log of y. And of course, the plus 8x equal 10 is still there. Now I just take the derivative term by term. I know the derivative of natural log of x. I know the derivative of natural log of y. I've got those formulas above. I know I can take the derivative of 8x, and I know I can take the derivative of 10. So if I can do those 1, 2, 3, 4 derivatives, I'm home free. Well, what is the derivative of the natural log of x? Well, it's just 1 over x. What is the derivative of the natural log of y? Well, y is a function of x, just like that u here, so it's going to be, instead of u prime over u, it will be y prime over y. What's the derivative of 8x? Just 8. What's the derivative of a number? 10's a number. A constant, 10, derivative is 0. Now I just want to solve for y prime. Probably the easiest way to do it is just multiply through by the LCD. You've got an x and a y in the denominator, so if you multiply both sides of the equation by x over y, when you take the x over y and multiply it by 1 over x, the x is canceled and you're just left with a y. When you multiply the x over y times the y prime over y, the y's cancel and you're left with x times y prime. And then when you multiply the 8 times the xy, you get 8xy. So when all is said and done, you get y plus xy prime plus 8xy equals 0, because xy times 0 is 0. And if you want to think of this as just multiplying everything by xy, however it takes for you to get that, in this case the x's cancel, in this case the y's cancel. And now I want to solve for y prime, so I want to move everything that doesn't have a y prime in it to the other side. And then I want to divide by the x, so I get y prime by itself. And if you divide both sides by x, you end up with y prime equals a fraction. The numerator is minus y minus 8xy, and the denominator is x. It's not so bad if you understand the basics and you don't forget the things you learned earlier, and you can follow them forward. These problems with finding the equation of a tangent line, we've been doing them for a long time now. It just so happens that this function has a natural log in it. It also happens that the second term of that function is a product. The 3x is like the u, and the natural log of x is like the v, so I know the product rule is going to fall in here. So when I take the derivative of 2, I get 0, but when I get to the 3x times the natural log of x, I've got to use the product rule. So that'd be u, which is 3x, times the derivative of natural log of x is 1 over x, plus, then I reverse it, natural log of x multiplied by the derivative of u, which is 3x, and the derivative of 3x is 3. So the x's cancel, the 0 goes away, the x's cancel and leave you with 3 in the next term, and then you typically put the 3 in the front, typically put the number in front just to make it look better, and you get 3 plus 3 times the natural log of x. That's the derivative. Why did we do the derivative? Because we want to find the equation of a tangent line, and an equation of a tangent line involves a point and a slope, and the derivative tells us the slope. So we've got to take the slope we just found, we've got to take the derivative we just found, think of it as a slope, and plug in the values they gave us at the particular point. Well, at the particular point, this is like the point x of 1, y sub 1. So x of 1 is 1. So you want to plug a 1 in for the x. The x needs an input, and the 1 is the x value. So you end up with 3 plus the natural log of 1, and then you got to say, oh, aha, remember the natural log of 1 is always 0. So I end up with 3 plus 3 times 0, which is 3 plus 0, which is 3. So the slope of this tangent line is going to be 3, and I know the point is 1, 2, so I go to the point slope form and I plug everything in. I plug a 1 in for x sub 1, I plug a 2 in for y sub 1, and I plug 3 in for the slope. And that gives me y minus 2 equals 3 times the quantity x minus 1. If I multiply the 3 through on the left, I get 3x minus 3, and if I add a 2 to both sides, I end up with the equation of the tangent line at the point 1, 2 being y equals 3x minus 1. It's the same thing we've been doing earlier. It just happens to have a log in it, so it comes into play. The new derivative rule for log comes into play at some point during this process.